This video is going to be going over integration by parts. So if you had a function that was a product of two other functions, we would have taken the derivative of that using our product rule, right? And so even though it might seem a little bit counterproductive, like it says here in the notes, one thing that you might want to do is integrate the derivative, and let's see what ends up happening when we do that. So h of x, which is that product of two functions, because this is a linear combination, I'm able to, or linear transformation with integral rules, integration techniques, I'm able to split up that integral into two integrals. And then if I want to then solve for this integral or the other one, we just choose this one, then I could subtract this piece over, and you can see that here. That's a lot of function notation. So most of the time we let f of x be u and g of x be v, which is kind of like a u sub in a way. So you'll say like, let u be this function, let g be this function, which means if we take the derivative of u with respect to x, then that would be f prime, and you can notice how we kind of write that notation with bringing the dx over here. Same thing with dv dx equals g prime, move the dx over. And instead of all of this notation here, we're going to use kind of some shortcuts. So we say the integral of u dv equals uv minus the integral of v du. Let's go ahead and look at an example. Now, back in the u sub type questions, this might have been the cosine of x squared. And then you'd be like, okay, composite function inside this is u because I had an x out here. Notice the derivative of the inside would be 1. It doesn't get rid of that x dx piece. So this is an example of when I would have to use integration by parts. So let u be the thing that when you take the derivative of it, it ends up going away eventually, meaning du is equal to 1 dx. The next thing we do is we let dv be equal to our other piece here, because I need to figure out what u is, and I need to figure out what dv is. So I'm going to let x be u, and I'm going to let cosine, x dx be my dv. If I integrate both of these, then I get that v is equal to sine of x. Notice then I can have this entire right-hand side, u v, so the integral of x cosine x dx equals u v minus the integral of v du. And the antiderivative of negative sign is something that we can find. It's going to end up being cosine. And then here's your constant of integration, because it is possible, right, that I could have that constant of integration so that when I take the derivative, I get back to sine. So you include it right there. All right, here's another example. Again, if you see e to the 3x, you might be like, oh, if I have just a 3 on the outside, or even if I don't, like we can make this u and do a u sub piece, but notice I have an x squared over here. Like that's not the derivative of the inside of an exponential function. I have to use integration by parts. Again, we're going to let u be the thing that goes away with the derivative, and I'm going to let dv be the stuff. Now, notice I said goes away eventually, because on this first one, it doesn't go away yet. The integral here is going to be 1/3 e to the 3x. And so I get the integral of x squared e to the 3x dx equals uv. I'm going to bring that 1/3 in the front. minus the integral of v du. So 2/3 x e to the 3x dx. I need to use integration by parts again because I can't take the antiderivative of this. Let u continue to be that same function. Let's take the 2/3 out here. Okay, so du equals dx. Now I'm going to eventually get that piece to go away. Dv e to the 3x dx. And so again, I get 1/3 e to the 3x as my antiderivative. All right, so this integral is equal to, I keep my 1/3 x squared e to the 3x minus 2/3, and then I have a second integration by parts here. So u v 1/3 x e to the 3x minus the integral of v du. All right, now this is something I can integrate without having to use parts. So I'm going to write my whole piece. X squared e to the 3x minus, when I distribute here, 2/9 x e to the 3x. Ooh, okay, positive 2/9. But then when I take the antiderivative of e to the 3x, I still need a 1/3. So we're going to end up having 2/27 e to the 3x plus c. Now there is a tabular method. There's a little bit of a shortcut method that you can use when you see that once you are going to end up taking u to be x squared, that you're going to have to do like multiple integration by parts pieces. So let me go ahead and erase all of this, and then I will show you how to do that. All right, so again, when I see like, oh, I don't just have an x cosine or an x e to the x, so I'm going to have to use parts multiple times. Usually that's when you have a polynomial larger than x to the 1, okay? You set up a table where your u's can kind of go in the left-hand side, and then your dv's can go in the right-hand side. And we're always going to choose the same function for our u's and our dv's as you do this multiple integration by parts. So you'll be able to kind of choose that same function and take the derivative until it runs out. So I'm going to use u equals x squared, 2x, 2, and then 0. Okay, that's what I mean by until it runs out. E to the 3x, then we take the antiderivative over here. Okay, so that these are all of my v's. Now this is your first u and this is your first dv. So in order to do the u times v, you do need to go on the diagonal. So that's your first u times v. Now remember, we're subtracting the integral of v du. So these are going to alternate signs each time. So you're going to have a positive, and then a negative, and then a positive, and then a negative. But your uv terms end up continuing to be on those diagonal pieces. And if you notice, that's the answer we got doing integration by parts twice. All right, let's go ahead and look at one more example here. Find the volume of the solid obtained by revolving the region bounded by e to the negative x, the x-axis, and the line x equals 1 about the y-axis. So let's go ahead and draw this. So here's e to the negative x, x equals 1, the x-axis and the y-axis. So I'm taking this piece here around the y-axis. So it's going to end up making a shape like this. Now we have two options. I'm actually going to use shell method here. And in our previous unit, you And I'm going to choose shell method because I do want to keep this in terms of x, and I don't want to have to split my region in terms of y. Like that feels really, really messy. So let's go ahead and take this and let's use shell method in order to create that volume. I'm going to draw my piece out here, okay, with a little thickness. So that's going to be in dx. I am going to integrate from 0 to 1. And the height of that is always going to be defined by my function height. And then the circumference, which makes up the bottom, is going to be, that distance is always x, right? So 2 pi x e to the negative x dx. Now, again, last unit, we would have said, write but do not solve, because you wouldn't have known how to integrate this, but now we know how to integrate this. So let's go ahead and do that. I'm going to do it with parts. I'm going to bring the 2 pi out here. And even when I only do parts once, I sometimes just like doing the table method. I think that it helps me organize my u and my dv. I see my u v's the whole time. So I personally just like using that table to organize it all. Okay, 2 pi big parentheses. Okay, first uv. Now remember, I have to alternate signs because this is minus the integral of v du. Now if I were to do that, that's great, but I have my integral of v du. It's e to the negative x here. And I'm going from 0 to 1. And then multiplying that by 2 pi. So 2 pi negative e to the negative 1 minus e to the negative 1 minus 0 minus e to the 0 is 1. So we end up getting okay, so negative 2e to the negative 1. I end up getting negative 4 pi over e. I'm going to go ahead and move that down. And then plus 2 pi. And that's going to end up being my final answer here.